Let me just quickly revise the few key definitions that were covered yesterday. I'm sorry, I forgot to save the file, so everything that I scribbled down is now gone. So I'll have to, it doesn't really matter. Okay, so let me just begin with some key definitions. First one was the set of all states for a single party system. And I chose to accept the convention that trace normalization is not really relevant for us. And so for us, quantum states are basically just D cross T matrices, which are positive semi-definite. And this is for a single party. And this has the geometry of a cone in a Euclidean space, for instance. And then we talked about pure states. These are simple kind of states that there are. And then we talked about these diagonalization and spectral decomposition. Every state can be decomposed. It's not really important for the second part of this talk. And then we talked about bipartite systems, right? So when we talk about bipartite systems, our Hilbert space becomes a tensor product of the underlying Hilbert spaces of the two particles. And when you talk about states of the bipartite systems, you need to talk about linear operators on this bipartite Hilbert space, and which for us in finite dimensions decomposes pretty nicely in this tensor product of the two separate matrix spaces corresponding to linear operators on the individual parties, right? And then the phenomenon of entanglement can be described in one equation, which is this one. So basically, if you take individual states of the two parties separately and then combine them in the sense that you take this product state and you can go a step further and mix them up together to get what is called a separable state. But these kinds of states form only a special subset of the class of all possible states of this bipartite system. And this is represented by this equation. You take the tensor product of the set of states of two individual systems separately. And this set is only a very strict, very small subset of the set of all possible states that can exist for this bipartite system. And hence we come up with the definition of entanglement, which we define in terms of something which is not separable. And how is separability defined? As I mentioned, if we have a bipartite state, it is said to be separable if you can find a finite number of states for the two parties separately, such that the entire global state can be written as a mixture of these product states, right? And if this is not possible for the given state, we say that the state is not separable, or in other words, it is entangled, right? And we can spectrally decompose these product constituents in the sum, and we can come up with an equivalent definition in which instead of arbitrary mixed states, we are in the sum, the constituents are pure states, right? And so this is the definition that we will be using in this latter half of the talk, in the second half. All right, and then we talked about how traditionally entanglement is detected, and this is where the entire theory of positive linear maps come into picture. If you have a separable state and you act on this partially by a positive map on only one of the subsystem, then what you get as a result is again positive semi-definite, and it's just a simple linear algebra, right? And then we discussed this important fundamental result in entanglement theory, which basically states that if you have a state of two parties such that for all possible positive linear maps from MD to MD, the partial action of this map on the state results in something which is again positive semi-definite, then we can be sure that the state that we started with was separable. So the only problem with this test is you have to check this for all possible linear maps which are positive, and this is an enormous set which is uncountably infinite, and so this is not really a feasible task. And so we need to come up with different methods depending on what kind of a we are in. And then we talked about one special kind of positive map which we are all familiar with, which is this transposition. Basically, this transpose map provides us with an entanglement detection test. We can apply this transpose map partially on any given state, and depending on what we get on the outcome, we can either get something which is not positive semi-definite, which implies the presence of entanglement, Or on the other hand, we can get something which is positive semi-definite, but notice that this doesn't tell us anything. And then we have to repeat this procedure for other positive maps until we find something for which this state is not positive semi-definite any longer. And then the specific map lambda, uh, for which identity tensor lambda, this partial action of a map on the state row, results in something which is not positive semi-definite. This is said to detect the entanglement present in the state row. And so transpose map provides us with one such example. And so in general, we can have states which are positive under partial transposition, but still they are entangled, and they are called PPT entangled states. And a lot of research has gone into finding new examples of such kind of states. And so this is like the general picture that we have for bipartite systems. We have the set of all possible states, which is this bigger ellipse here. I've just drawn it as an ellipse. It's a convex cone for us, right? And one subset of this is the set of positive partial transpose states, PPT states, and then further in we have even smaller set of separable states, right? And then for qubit systems, there is a special, this transpose map plays a very special role in the sense that separability for qubit systems is equivalent to positivity under partial transposition. So you need not check positivity of this state under all possible partial actions of all possible positive linear maps. You need to just check it for one map, and then you're done. So in qubit systems, the problem is basically solved. But for d greater than or equal to 3, you need to you run into trouble, right? So this was what we did last time. And then
I had a question.
yeah,
So for d greater than 3, is there any way to reduce uh, the number of maps you have to apply from uncountably infinite to a countably infinite? Like say,
I don't think so. So that
for
helps.
any special case.
So you need to, in general, it's not possible, and that's why the theory is difficult. In general, you have to perform some kind of a search in this entire space of positive linear maps, which is like trying to find a point in a ball in a three-dimensional space, right? And you can imagine that how difficult that is. But depending on what situation you are in, you can employ some kind of a symmetry argument or some additional information that you have for the state to reduce this search space suitably. And so in certain instances, it's possible. And for very special kinds of states, which are highly symmetric, this task becomes easier to perform. But in general, it's something called this problem of detecting entanglement. Complexity, theoretically speaking, is NP hard. And you can look it up, this definition of NP hardness, in classical complexity theory. But in general, the problem is hard. And you can only reduce it to easier problems if you have extra symmetry conditions or some extra information about the state. And that is what we are going to do now in the second part, partially. All right.
Yeah, thanks.
Thank you for the question. Okay, so this is where my research comes into picture. So as I said, the problem is difficult, tremendously difficult in general. And as is often the case in physics, if you have a difficult problem, you try to simplify it by invoking some kind of a symmetry of the system, right? And that is what we're going to do now. So I define a new kind of state, bipartite state, which I call local diagonal orthogonal invariant, or LDOI for short. And this is a special kind of state which satisfies this property. So what you're doing here, you are taking the state and you are conjugating it on the left and on the right by local orthogonal matrices. So this O matrix here, this is a D cross D matrix, which is diagonal. And on the diagonal, it can only have plus or minus one entries. So it's orthogonal and diagonal at the same time. So the entries, everything else is zero, right? And on the diagonal, it can only differ in sign, right? It can either have plus one or minus one as its entries. And I demand that the states, this LDOI states, are such that the action of this diagonal orthogonal group, this local action of this group on the state, makes this invariant, in the sense that if you apply this diagonal orthogonal matrices on the left and on the right in this fashion, the state stays invariant. And you can imagine that this property will not be satisfied for all possible states. And so that's why this is a non-trivial definition, right? And so this is like a symmetry for the system. This state is invariant under the local action of the diagonal matrices. And the way to characterize this kind of states is as follows. So let's just consider very simply the standard basis units of the MD tensor MD space, right? So we saw yesterday that, let me just draw them with some space in between. Okay. So these were the basic matrix units that form an arbitrary matrix in MD tensor MD, right? What we're doing here, we are applying orthogonal matrices on the left and on the right for both of these tensor factors, right? And then from the form of this orthogonal matrix, it is clear that if you act this orthogonal matrix on a basis vector, let's say this I ket, then what you get is the same thing again, but with a sign difference. I hope that's clear, right? So it's like you have in the 3x3 case, let's say we have this kind of an orthogonal matrix and everything else is 0. And you act on it on, let's say, this 2 ket. So that will be 0, 0 here and 1 on the middle. And it's clear that since on the second factor we have -1 here, this will be 0, -1 and 0 again. So it's basically the same ket again with the minus sign. And if you apply it to 3, which will have 1 on the bottom index, then this will basically be 3 again, because there is a +1 here, right? So in general, you can act on this orthogonal matrix on this basis ket, and you can get, and the result will be plus or minus the thing that you started with. And so what we basically want to achieve here is we want to see what kind of these matrix units, when one applies these local orthogonal operations on both tensor factors, what kind of matrix units stay invariant, in the sense that, so if we apply these orthogonal matrices, we have just seen that we will have some plus minus sign here, plus minus sign here, plus minus sign here, plus minus sign here. And our task is to determine what kind of matrix units are such that these signs that arise when you act upon, and when you act by the diagonal orthogonal matrices, they cancel themselves. And you can imagine that if these signs will cancel themselves if we pair the indices up. So in the sense that if on the first factor both of these are I, and so there can be two possible cases. Either both of these accumulate a plus sign, in which case this thing stays invariant, right? Or in the second case, both of them will accumulate a minus sign, which will again get cancelled, right? So we can reformulate this problem of finding states which stay invariant under the local diagonal orthogonal action in the following manner. So we have these 4 bras and kets here, right? So let's just represent them as points. And what we want to do is we want to pair them up. So there are 3 possible ways to do that. You can either do this, so that will correspond to a matrix unit of this form, I, and then this is some JJ, right? In another case, what you can do is you can pair, let's say, this and this, right? This will correspond to IJ tensor I again NJ, right? So these two are the same indices and these two are the same indices. And the final combination can be when you pair, let's say, the middle two, right? This will correspond to the case when you have IJ and JI again. And these are the only possible cases. And in general, you can take arbitrary linear combinations of these matrix units, and the result that you will get will be invariant under this kind of a linear operation, this kind of a local orthogonal action. So is this part clear?
I have one doubt. Sorry, maybe I'll just go ahead. I was just curious. These 3 cases make sense to me, but how do you know that these are the only possible cases? For example, if I have an II on the left, but on the right hand side I have KL, and I have some different KLs, and those also cancel each other.
you have something like this where these are not equal, right?
Yeah.
The important point to note here is that this should hold for all possible diagonal orthogonal matrices. So if these
Oh, I see.
are different, you can come up with a O such that O acting on K will have a minus sign and O acting on L will have a opposite sign. Then
Oh,
this thing will accumulate a total minus sign.
okay, that makes sense. So it should be valid for all O's, and
Yes.
these are the only cases where
Yes.
it's valid for all O's.
Yeah. In order for this equation to hold for all orthogonal matrices,
These are
you
the
pair these up in pairs of 2. And if there is a single index which is not paired up with anything else, you can find an O for which this index will cause trouble. It will lead to a total minus sign or plus sign or whatever.
right. Yeah, that makes sense. Thanks.
Yeah.
Yeah.
All right. So we can only have these kinds of basis elements. And so we come up with a nice theorem. So this is like a characterization of local diagonal orthogonal invariant states. So notice that in deriving this result, we never talked about positivity. So positivity of the state will have to be imposed separately from this, right? And so basically the result is this. So a bipartite state of the system is said to be LDOI or local diagonal orthogonal invariant. I mean, it's not said to be, it is LDOI if and only if it is of this form, where these matrix units are just the ones that we derived, right, a couple of minutes ago. And notice that we can have arbitrary complex factors alongside these matrix units and then just sum them up. And so if you apply O orthogonal matrices on all of these factors, it's clear that the signs that come up will cancel each other. And the thing that you get is invariant under the local action of the orthogonal group, right? And then what are these conditions here? So these conditions ensure that the state that we have here is positive semi-definite. So notice that in these three combinations that we talked about earlier, it might be the case that I is equal to J in the sense that all of them are connected, right? And that can happen in all of these three cases, right? You can just you need to just connect this and this. So, but that we need to count this case only once. So what we do is we take the convention and count this case in the first sum. Notice that there is no constraint on I and J in the first, so I and J can run freely from 1 to D. In particular, they can also be equal, right? But if you notice the second and the third sum, we by hand impose the constraint that I should not be equal to J. Because if I was equal to J, then basically we would be counting the same case another time, one more time. And that's why we by hand put this constraint that for the second and third sums, these basis vectors, these I and J indices are not equal to each other, right? And so this state is basically parameterized in terms of three matrices, A, B, and C. These are D cross D matrices. And this is the condition. This is the first condition, that they must have the same diagonals. And this is basically got to do with the fact that if you look at the second and third terms, the diagonal entries of B and C are not even being used, right? Because we are only summing over indices which are not equal. So we are only using diagonal entries of A. And so we, by hand, adopt this convention that these two matrices B and C that come up in the second and third sums, they have the same diagonal as the first one. So this is just a notation, or you can say a convention that we employ. And the second set of conditions, these are important. These are necessary to ensure that the state that we get here is positive semi-definite. So notice that I'm using a different curly symbol here. This means that A is entry-wise non-negative. And what do I mean by entry-wise non-negative? Basically, all the entries of these matrices, of this matrix A, are non-negative. And B is the usual, B is positive semi-definite. C is in particular Hermitian, and certain entry-wise inequalities must hold between the entries of A and C. So these are not really important. These can be derived with not too much effort. So I'm just stating the conditions here and not worrying about how one can derive it. It's an easy exercise. And so these are the two sets of conditions on the matrices A, B, and C, which guarantee that the corresponding LDOI state is positive semi-definite. So in particular, I mean, for us, positive semi-definiteness is equivalent to the matrix being a quantum state, right? So
Satvik, one question here. Just the statement you mentioned. So we call something a state if it is positive semi-definite, no?
yeah,
So here, let's say the set of states that are LDOI, how would you, so in this set of states that are LDOI, there are things that are not states as well.
yeah, there are things which are not positive semi-definite, and they will precisely be the ones for which, let's say, B is not positive semi-definite. If you put such a matrix in this expression, you'll get something which is not a state. It will just be some matrix,
Right.
but it will not be positive semi-definite. Yeah.
Right. So you're only interested in those the states
Yeah.
that
So
are
since we are interested in quantum mechanics, we only
states,
need to look at. I mean, all this entire thing of entanglement is only relevant if we talk about states.
states, right?
Right. We talked about the cones of the states, right, and tensor product and so on. So,
Right.
so we are only interested in positive semi-definite matrices, and these conditions ensure that the state that we have here is indeed a state. It's positive semi-definite, and just to recall or restate that this sign means that A is entry-wise non-negative. In addition, if we impose that the state is also positive under partial transpose, then we'll have further sets of constraints, right? Because a positive semi-definite matrix need not be positive under partial transposition. So if the state is on top of being a state is also a state which is positive under partial transposition, then the C matrix, which was originally only Hermitian, it also needs to be positive semi-definite. And these entry-wise inequalities between A and C matrix must also hold between the entries of A and B, right? So these are just, these can be derived. It requires some effort, but it's not too difficult. All right, so this is like a characterization for LDOI quantum states, right? And now it's natural to ask whether we can say something about separability of these states, right? And the next theorem is okay. So before separability, let us just quickly look at a typical 3 tensor 3 LDOI state. So this lies in M3 tensor M3. So this is like a qubit state. And so you can see that the A matrix that we had earlier, this is basically the entries of the A matrix occupies the diagonal entries of the big row. And the B and C matrices occupy some of diagonal positions here. And everything else, these dots, they represent zeros. So everything else is zero. So you can imagine that this is a very special class of matrices, right? Which has lots of zeros in it, and only very specific entries in this matrix are non-zero. And this big LDOI, so this is a 3 tensor 3 matrix, and this is parameterized by 3 matrices, which are also of dimension 3, right? And this is just, and you can show that this same kind of a structure holds for arbitrary D tensor D LDOI state, right? So this is just for illustration in order to get a feel of how the state looks like. All right. Now we address the question of separability of these states. So to recall, this is the definition of separability that we earlier used, right? State is separable if it can be represented as a mixture of pure product states, right? And so what we now do is, let's say we have an LDOI state, right? We just saw that it can be written in this fashion. We have an A matrix in the first factor, which is like this, right? And then we have a B matrix with certain things, with certain matrix units, and then a C matrix, right? And then we just say that, let's say that this is separable, right? So this is also equal to a state of this form, VK, and tensored with WK, WK, where these V and Ws are some arbitrary vectors, right? And then what we can do is we can get expressions for these A, B, and C matrices in terms of the vectors that we used in the separable decomposition, right? That seems like a valid task. We have an LDY matrix. We know its general form, and its general form is given in terms of these three matrices, A, B, and C. Now, what we are doing is we are assuming that, let's say, the state is separable. So we can set this expression to be equal to some separable decomposition. And then our task would be to, from this decomposition, from this equation, write down A as some function of these vectors V and W. Similarly for B as some functions of these vectors, and C, well, these can be different functions, it's not the same, as some functions of V and W, right? And if you sit with this problem for a while, then this theorem can be derived. So this is the main result. This LDY state rho, which is parameterized by these three matrices A, B, and C, this is separable if and only if the matrices which parameterize this state can be decomposed in this fashion. So A is a sum of these rank 1 states, similarly B and C. Notice that this what is this symbol here, and this is new, right? I did not define this before. So for two vectors, let's say we have two vectors V and W, which are of this form. So this circle with a dot inside it, this is an entry-wise product, in the sense that you just take the entries and multiply them entry-wise. So this would be V1, W1, V2, W2, right? So this dot represents entry-wise multiplication of vectors. And so A matrix, for the A matrix, you're taking a vector and you're multiplying it with its own complex conjugate. And so this will be something non-negative. This vector will have all its entries, all of the entries of this vector will be non-negative, and similarly on the right-hand side. And so a typical factor in the decomposition for A matrix would be something like this. So on the left, we have mod V1 square to mod VD squared, let's say, and we have a bra vector, which is of this form, W1 squared dot 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 WD squared. And we can this is sum over different kinds of these kinds of units, right? So clearly, since all of these entries of these vectors are non-negative, this A matrix is again entry-wise non-negative. All of the entries of A will again be non-negative. And for B and C matrices, the decomposition consists of pure states, right? So these are some vectors, and we are just taking the bra vector, and then this is like a pure state in the sense of quantum mechanics, right? So, and then we are taking a sum. So the final thing will be positive semi-definite in particular, right? And similarly for the C, it's again a state of this form. So this thing will again be positive semi-definite again. And in particular, the entry-wise inequalities that we earlier talked about, which were of this form, right? Aij, Aj bigger than or equal to mod Bij square, and similarly for mod Cij square. These will also hold, and one should expect that this should hold, because if you recall, these inequalities, these inequalities were used to characterize a set of states which are positive under partial transposition, right? And in particular, separable states are positive under partial transpose, right? And they are also positive semi-definite. So this is the characterization of separability for local diagonal orthogonal invariant states, right? And now you can, I mean, on the face of it, it looks like we've just made things more messier, right? We originally had a definition of separability, and now we have these three different matrices which are related in some sense, and they admit these kind of a decomposition. So it seems on the face of it, I mean, what have we gained? We have just reformulated the problem in a different way, right? But the upshot of this whole procedure comes into picture when we bring in the notion of graphs, and in particular triangle-free graphs, which is what we are going to do next. So before we move on, are there any questions on this theorem? All right, everything is clear? Wonderful. Okay. So now we come to the notion of triangle free states. And before doing that, let's just recall again the general form of LDOI states that we had, right? And now what we do is, let's say we have a general 3x3 matrix, right? Just 1 second here. Okay. Which is something somewhat like this, right? So we have 3x3 blocks, right? So all of these are 3x3 matrices in themselves. And this is a big matrix, which is 3 tensor 3 matrix, let's say. Now, what we do now is we take the diagonal entries from this matrix and then place them as rows of a new matrix, which we call A. So basically what we are doing here, we are just collecting the diagonal entries and then putting them as rows of a different matrix, which we just choose to call A, right? And for instance, if we do this procedure for an LDOI matrix, what we will get is just the A matrix that we have here, because the A matrix occupies the diagonal, right? So we define for an arbitrary bipartite matrix in MD tensor MD, we define a corresponding matrix A, which will be a D cross D matrix, entry wise in this fashion. So basically what we are just writing this equation basically says that we do this procedure here. We take the diagonal entries and collect them in the form of these rows and call it the A matrix. This can be done for any bipartite state, right? Now, once we have this matrix, we associate a network or a graph to this matrix in this fashion. So what we do is, since we are in D tensor D and this A matrix is a D cross D matrix, the graph that we associate will have D vertices inside it, right? So we can imagine something like we draw points in a plane, right? And there will be D of them if we are considering D cross D states. And let's say we label these vertices I, J, K, and whatever. And then we need to draw some connections between these vertices. And the rule to form these connections is as follows. So we draw a line between I and J, ith and jth vertex, if and only if the corresponding entries in the A matrix, Aij and Aji, are both non-zero. Right? So you can imagine that we first just draw these points on the plane and then we label them 1, 2, 3, 4, 5, 6, 2, ... D, where D is the dimension that we are considering here. And then we case by case, we look at pairs of these vertices. Let's say we take 1 and 3, and then check whether the A matrix that we constructed, the A13 and A31 entries, whether they are both non-zero. And if that is the case, then we connect the 1 and 3 vertex with a line, right? So this is a typical example of what a typical graph would look like. Let's say the A matrix looks something like this, where whenever I say A12, A13, all of these are non-zero, and the only zero entries are these two, right? So what we do is this is a 4x4 matrix. So we draw a graph which has 4 vertices, right? And then we connect these vertices by lines, and notice that these 1 and 3 and 2 and 4, these are not connected by a line because the 3-1 entry and the 2-3 entry are 0, right? I hope this is clear. And everything else is connected because for the 1-2 entry, 1-3 entry, 1-4 entry, and all of the other entries are non-zero. And so all of these connections are valid. Just these two connections, 1 cannot be connected with 3 because we have a 0 entry in the third row and the first column, right? And similarly, 2 and 4 vertices, they cannot be connected because we have a 0 entry in this position. This is clear, right? So this is just a procedure that we have. We can now, given any bipartite state, what we can do, we can collect its diagonal elements in this matrix A, right? And then we can form a corresponding graph for this matrix by following this rule, right? And then we define a state to be triangle free if the graph that we just constructed has no triangles in it. So for instance, in this example, if 2 and 4 were connected, we would have 2 triangles here. But since that is not the case, this is triangle free. And hence the corresponding state row from which this graph was constructed is triangle free by definition. This is our definition for what it means for a state to be triangle free. All right. Are there any questions in this part?
Just to confirm, so whether or not a density, a state is triangle free is only determined by its diagonal entries.
It is determined by the zero pattern that is present in the diagonal. So if you so this graph is basically determined by where zeros are located in the matrix, right? So
Right.
the graph is entirely determined by how zeros are distributed on the diagonal of the state that we started with.
Right. Right.
The property of a state being triangle free is a property of the zero pattern of the state's diagonal.
Right. Okay. Okay. And
All
nothing else. So I mean,
Yeah.
all other
Yeah,
elements of
nothing
the
else. Yeah, we don't care about anything else. This is just solely a property of how zeros are distributed on the diagonal of the matrix of the state that we started with. And the problem of detecting whether a given graph is triangle free or not, it's easy in the sense that the time that it takes for an algorithm to determine whether or not a D vertex graph is triangle free, it scales polynomially with the D. So it's easy. It can be checked very easily.
Right.
All
And
right.
that makes sense because I just have to calculate these diagonal, these Aij elements.
Yeah. Basically, what you have to do, you have to take triples of vertices I, J, and K. And what you have to do is you have to check this product Aij, Aj, K, A, K, I. And if this is non-zero, then basically you have a triangle formed between the I, J, and K.
Oh, I see. Okay. Right. Okay.
And
Okay.
you need to do this for all triples of vertices. And that's it. And it can be done in polynomial time in the number of vertices, right? So it's an easy problem. So
Okay.
we know we have a notion of triangle freeness of states, and we can check it very easily. Given any state, we can determine quickly whether or not it is triangle free,
Okay.
right? And then now let's just quickly look at some examples of states and their graphs. So let's say our A matrix is of this form. Let's say we are considering 3x3 matrix, and it's a matrix of this form. Let's say we have these kind of vectors here. So this is a ket, let's say V, and this is a bra, let's say W, and there are some entries 1, 2, 3, 4, 5, 6, let's say something like this, right? And then if you compute this matrix, you will have a 3x3 matrix in which all of these entries are non-zero, right? You just multiply them together. And so the corresponding graph will basically be a triangle because everything is zero. So this will be a 3-vertex graph, and all of the vertices will be connected with each other because everything is non-zero here, right? And in general, if you have let's say a D vectors of length D in which, let's say, 3 entries, 3 positions are common between these 2 vectors for which there are non-zero entries present, right? Let's label these indices I, J, and K. And we don't care about what else is present here in these 2 vectors. So this is a matrix A of the form ket V bra W, and where V and W share non-zero entries at 3 common indices, which we call I, J, and K. So if you form the graph of this matrix, this will be a D vertex graph. There will be lots of vertices here, but we don't care about in all arbitrary vertices. We just look at the 3 vertices, which we can again be sure that between these 3 vertices, there will be a triangle. So whenever we have a matrix of this form, if V and W share non-zero entries at 3 common indices, then the resulting matrix will have a triangle inside it, and the triangle will correspond to the 3 indices I, J, and K. Right? This is also, I guess, pretty straightforward.
So I just want to confirm something. Sorry to interrupt. So in general, I expect a state to not be triangle free.
Yeah, there is no reason. It's a special property of a state. Okay, now we come at the crux or the core of this talk, where we talk about where we use this fact of triangle freeness with the LDOI property that we earlier defined to come up with a nice strategy to detect entanglement, right? We just have to talk about one prerequisite, which is the notion of comparison matrices. So this is just a definition for any D cross D matrix B. Its comparison matrix is defined to be another D cross D matrix for which the entries are defined in this way. On the diagonal, what you do is you just take the absolute value of the original entries. And on the off diagonal part, you just take the absolute value and flip the sign. So if you have something like, and let's say e to the power I theta or something, then let's say this is minus. So the comparison matrix will, on the diagonal, everything will be positive because you take the absolute value. And on the off diagonal, you take the absolute value of this, which will be 1, and then you take a minus sign. So this will be -1 and something like, and depending on what other matrix entries are, you can easily form the comparison matrix, right? And why do we introduce it? We will see it shortly how this is why this is relevant. But we just know two facts about these matrices. If you start with the matrix which is positive semi-definite and you compute its comparison matrix, in general, the comparison matrix might not be positive semi-definite again, because you're changing the entries, right? You're putting minus signs on the off diagonal and doing stuff to the entries. So there is no reason for the comparison matrix to again be positive semi-definite if you originally started with a positive semi-definite matrix. But for two-dimensional 2 cross 2 matrices, you can think of a typical 2 cross 2 matrix like this, right? Where A and B are non-negative, and the determinant of this thing is also non-negative. So in 2 cross 2 matrix, this is a typical form of a 2 cross 2 Hermitian matrix, right? And if you impose positivity on top of hermiticity, you get these two constraints, which are very easy to derive. The diagonal entry should be non-negative, and the determinant of the matrix should be non-negative as well. So let's say if you then compute the comparison matrix, since originally the entries on the diagonal were positive, so they stay unchanged. And on the off diagonal, you get mod C and mod C with the minus sign, right? And so if you again calculate the determinant, it's basically the same thing. And it will again be non-negative. So in 2 cross 2 cases, 2 cross 2 matrices, if you originally start with something which is positive semi-definite, then the comparison matrix will again be positive semi-definite. But you can imagine that if D is bigger than 3, for 3 cross 3 matrix, a simple example suffices to show that this is not really the case anymore. So this is the B matrix, and it is easy to see that this is positive semi-definite because B is like a pure state of this form, right? And then once you compute the comparison matrix, it will be 1, 1, 1 on the diagonal and -1 everywhere else. And it is easy to see that this matrix will have a negative eigenvalue. So in dimension 3 and larger, if you start with the positive semi-definite matrix, the comparison matrix need not be positive semi-definite. And this is a very strong constraint on the set of positive semi-definite matrices, in the sense that if you impose by hand that a positive semi-definite matrix is such that its comparison matrix is also positive semi-definite, it's a very strong, it's a strong constraint on the class of matrices that you're considering. All right. Okay. So now we come to the main part of the talk, and basically we are combining everything that we just studied till this point and coming up with this theorem. So let's look at the ingredients of this theorem. So we have an LDOI state rho ABC, which is parameterized by these three matrices. On top of this, we assume that the state is triangle free. So the graph of the A matrix that we consider, it has no triangles inside it, right? And we assume that the state is separable. So we combine these three assumptions, and then the claim is that if you compute the comparison matrices of these B and C matrices, then they will both be positive semi-definite. And we just saw that this is a strong constraint on the set of positive semi-definite matrices, right? In general, for a separable state, there is no need or for a general quantum state, there is no need for comparison matrices to be positive semi-definite. So this is like a manifestation of this property of separability in the form of positivity of these two matrices. Right. So this is a necessary condition for separability. If you start with something which is LDOI plus triangle free plus separable, this implies that the matrices that define this state are such that M of B and M of C are positive semi-definite. So this is a necessary condition for separability of triangle-free LDOI states. Since we know initially that the state that we are considering here is LDOI, right? And we have already seen a characterization of separability for LDOI states. So what we can do is we can find, since the state is LDOI and separable, there exists a collection of vectors V and W such that the three matrices can be decomposed in the fashion that we saw earlier, right? A will have something like this, a decomposition of this form. And similarly, B will have something and C will have something, right? So in step one, we just use the information that we originally started with an LDOI matrix, and which is separable also. And using that, we can write
Satvik, what is TCP decomposition? What is the full form?
I think I forgot to mention. So when the three matrices that correspond to a separable LDOI states, so these three matrices when these three matrices can be decomposed in this fashion, we say that this matrix triple ABC is triple wise completely positive, which is abbreviated as TCP. So this is in some sense a generalization of an already existing notion of complete positivity for matrices for matrix triples. So that is why this naming, that is why I call them triple wise completely positive. It's not really relevant for our purposes. We just need to know that if a state is separable, then the matrices can be decomposed in this fashion. Now, where does this property of triangle freeness come into picture? So let's assume that in this sum, there is some index k such that there are three common entries between the kth v vector and the kth w vector, right? At three indices, they both of these vectors share non-zero entries, right? If that is the case, then if we form this outer product, then by following the same logic as before, we can conclude that if these are the I, j, and k indices, right? Then if you draw the graph for this outer product, the I, jth, and I, j, and kth vertices will contain a triangle, right? But that is not possible because we originally started with something which is triangle free, right? So what can we conclude? We can conclude that V and W vectors cannot have common entries, common non-zero entries at more than two locations, right? And this is like this is how we state it. Using the triangle freeness of A, we conclude that the support. So for any vector V, its support is basically collection of all indices where the entries are non-zero. And we have just seen that the triangle freeness of the graph can be used to show that the common support of these two vectors, V and W, should not be of size more than 2. Right. So this is where the assumption of triangle freeness comes into picture. We have just shown that for each, and I have not probably mentioned this before, this is true for every k. For every k, the corresponding vectors Vk and Wk can have a common support of size at most 2. If it was of size greater than 2, then the A matrix will have a triangle. Is this part clear? This is like the most crucial step where this entire business of triangle freeness is coming into picture.
Satvik, so we imposed this, like we had this condition initially that our row is triangle free And then when we do the TCP, the triple
Yeah.
completely positive decomposition, then how do we know for sure that A should also be triangle free?
So the definition of triangle free was in terms of A only, right? So how do we,
Okay.
how the state was defined to be triangle free if the corresponding A matrix is such that its graph is triangle free. That is how we defined it, this notion in the first place.
Okay. Mhm. Right.
All right. So there is still one thing left. We have shown that the common support of these VK and WK can be of size at most 2. And then we still need to show that these matrices are positive semi-definite, right? But then you can imagine now how the proof would proceed, because from the TCP decomposition, we know that B is of this form. And we have shown just now that all of these constituents present in the sum are such that the support of these are of size at most 2, right? So at most they can have 2 non-zero entries. And we have also shown that for 2 cross 2 matrices, if something is positive semi-definite, its comparison matrix must also be positive semi-definite, right? And so since all of these constituent elements in this sum are 2 cross 2, basically 2 cross 2 matrices, which are positive semi-definite, their comparison matrices will also be positive semi-definite, so that the whole thing is also positive semi-definite again. I mean, the entire comparison matrix is positive semi-definite again. And this notion of triangle freeness is coming into picture in this step to show that the common support is of size at most 2, which when combined with the fact that for a 2 cross 2 matrix, positivity of a matrix implies positivity of the comparison matrix. These two facts combined together show that this entire B matrix is positive semi-definite. So this is the essence of the idea. You can sit down and do everything explicitly, and you can refer to the paper if you want details, but this is for how the proof proceeds. And the upshot of it is that we have now managed to obtain a very powerful necessary condition for separability of triangle-free LDOI states, which we can now exploit to devise a nice entanglement detection strategy for these states. This is like the main result of the paper. And basically what we are doing here, you can consider this result actually holds for states which are not LDOI as well, in the sense that any arbitrary state can be considered here. But for to begin with, let's say that we have an LDOI state, which is of this form, right? The most general form of LDOI state. And let's say this is triangle free, right? So this is easy to check. You just need to collect the diagonal entries from the A matrix, draw its graph, and check whether that is triangle free or not. So this step can be easily checked. This condition can be easily checked. Then what we do next is we check whether the B and C matrices are positive semi-definite or not. If it so happens that either M of B or M of B or M of C is not positive semi-definite, then by employing the previous result, we can be sure that the state is entangled, right? Because if it was separable, then these matrices must have been positive semi-definite. And positivity is again easy to check. You just need to compute the eigenvalues. So we have basically reduced the entire formalism of the entire theory of positive maps, positive linear maps, and so on, the procedure of checking whether or not there exists a witness positive map which detects the entanglement for any given state. We have gotten rid of the entire formalism and instead developed a new formalism, which the only extra ingredient in this formalism is this notion of triangle freeness, which obviously limits the domain of applicability of this result. But within this constrained set of states which are triangle free, where we have a nice way to detect entanglement, what we need to do is just look at the B and C matrix which defines the state and check whether the corresponding comparison matrices are positive semi-definite. And this is computationally very easy to do. You can do it in a second on MATLAB. And If that is the case, then you can be sure that the state is entangled. And this is for LDOI states. This can be easily extended to work for arbitrary states which do not have the LDOI property to begin with. But for that part, we need to talk about some extra stuff, which I don't think would be very insightful for this talk. You can look the paper up if you are interested. But the main is that.
Satvik, just because you're talking about this, how easy is it to check if a state is LDO? If I give you a random state, how easy is it to check if it is LDOI? Maybe I didn't catch it.
Right, you just need to look at the matrix, right? We explicitly saw the form of the LDOI matrix. If there is a non-zero entry in any one of these indices, then the state is not LDO.
Oh, okay, there are.
That's
Okay,
simple as that. Yeah.
okay.
Let me just say a few words about how this test can be extended to non-LDOI states. And so the essential step is that if you start with any arbitrary D tensor D state, then you can actually map it to an LDOI state by performing a local operation. What you do is you basically take these orthogonal matrices, right, that defines the LDOI state, and perform like kind of an average over all, let me just call it average, over all diagonal orthogonal matrices, where this procedure of averaging needs to be properly defined. But the idea is that you start with an arbitrary matrix and you conjugate it on the left and the right by these diagonal orthogonal matrices. And then you perform like an averaging over this entire set of diagonal orthogonal matrices. And then you can be sure that the result that you get will be invariant under this diagonal orthogonal operation. So it will be LDOI.
It's a finite set.
Yeah, this is the finite set. So this is like, what is the diagonal orthogonal matrix? It's a D cross D matrix with plus minus one on the entries, right? So if it's a D matrix, then there is like two possible choices for each diagonal entry, right?
Yeah.
So this will be like 2 to the power D number of diagonal orthogonal matrices. So you can easily perform the averaging. You can just you can put a uniform measure on this set. You can say that every orthogonal matrix can occur with probability 1 over 2D. And then what we are basically doing here is you are computing the sum. You are summing over all diagonal orthogonal matrices with an extra weight of 1 over 2D. And if you do this sum, then you can be sure that the result that you get will be LDOI because of this averaging operation. And the most important point of this step is that this is a local operation, in the sense that the operation that if we start with an separable state originally, then the thing that we get after performing the averaging will again be separable, because we are only acting locally on the two systems and then summing things up. So if we originally started with a separable state, then after performing this averaging operation, we will get something which is again separable. We will get a separable LDY state. And then we can use the non-positivity of the B matrix and the C matrix to conclude things about the entanglement and so on. So this is how you would extend this strategy to arbitrary states by invoking this averaging procedure. But let's not go too deep into this. All right. So basically, this is the main result. And if I guess it would be, if there are any questions before moving on, I would be happy to answer them. Are there any? So this is like the fundamental. This is the main result of the paper, and then we are just going to talk about a few consequences of this result, and using this result, we can basically devise a protocol of constructing new examples of states which are entangled and PPT and so on. So that will be the last part of the talk. Before moving to that, if there are any questions on this part, I will be happy to answer them. All right, so I guess there are none. So, okay, so let me just quickly talk about a few consequences of this result. So basically, imagine this. We ask a child to draw a bunch of points on a piece of paper, and then join them up and then ask him or her to join them up with some vertices or some lines, right? Some edges in such a way that the resulting figure does not have any triangles inside it. So a typical, like, let's say this is what he or she comes up with, or let's say this is another example of a graph which does not have any triangles, or this, or let's say this, or this big mess. So all of these are examples of graphs which do not have any triangles inside them. And the remarkable thing is that we can take this figure, which is a graph with no triangles inside, and then translate it or transform it into a family of entangled states, rho A, B, C, which are LDOI. And these will be entangled states in MD tensor, MD, some bipartite space, where D will be the number of vertices that this graph has, original graph that we started with have. And now I will basically just tell you a procedure to do this. I will tell you a protocol which can be used or applied on any triangle-free graph to come up with a corresponding family of entangled states. So let's just first recall, or this is the main, basically this is the essence of the paper. If the state is LDOI and triangle free, then these two matrices should be positive semi-definite. This is the crux or the core of the paper. So so we can reverse engineer and try to see if we can, using this result, we can construct or we can come up with a procedure to compute or define entangled families of states corresponding to any graph that we have. So the step one would just be to come up with a graph which is triangle free. So let's say for a simplicity, we have a 4-vertex graph that we saw earlier, like the square. This obviously does not have any triangles inside it, right? So this is step one. You just come up with your choice of a graph which is triangle free, right? So and then the next step would be to come up with matrices A, B, and C, which for in this instance would be 4x4 matrices. So the dimension of the matrix should be equal to the number of vertices in the graph that you started, right? And these matrices should be such that if you form the graph of these matrices, graph of A is equal to graph of B is equal to graph of C is equal to the original graph that we started with. Basically, this is a constraint on the zero pattern of this matrix. You only choose certain matrices which have a special zero pattern which corresponds to the graph that you started with, right? Now, the crucial step is that you can pick either B or C, whichever one you like, and try to find an example or search for a B matrix which is positive semi-definite. But at the same time, the comparison matrix of it is not positive semi-definite. So this is the third step. And basically this ensures that whatever we build next, whatever state that we come up, that we construct in the next step, will violate this necessary condition of being separable. And so we are in the step 3, we are basically inputting the information for the state to be entangled. And the next step would be the final step would be to make sure that A is entry-wise non-negative and C is also positive semi-definite, and the other entry-wise inequalities that we earlier saw, all of these should hold, and so on. So this is basically the procedure. You start with this graph which is triangle free. You construct 3 matrices for which the graph is equal to the graph that you started with. So we say that these are matrix realizations of this graph. So a matrix is said to be a realization of a graph if the graph of that matrix is the graph, right? And this is the crucial step which ensures that the state that we come up with is not separable. And then the final step is just formalities to ensure that the state that we come up with is positive semi-definite and so on. And so the result, you will have LDOI state which corresponds to these three matrices that you considered. This will be a bipartite state in M4. So for instance, here we are considering a 4-vertex graph. So this would be a state in M4, tensor M4. And this will be entangled, a triangle-free entangled state. And on top, if you want to impose PPT condition, then you can impose the fact that Aij, Aji is also bigger than or equal to mod Bij square. So whatever property that we earlier discussed about positivity and positivity under partial transposition, you can use them in the step 4, in the 4th step, to ensure that the state you construct have the desired property. So for instance, if you ensure these conditions, then the state that you come up with in finally, so let's say this is step 5 or something. This will be step 3 will guarantee that this is entangled. Step 4 will guarantee that this has all the required properties for it to be a state. And so you basically will have an example of a state which is triangle free, entangled, PPT, and whatever else, whatever other property you require. Right, and notice that this will have a lot of free parameters inside because A, B, and C, these are matrices, D cross D matrices. So there will be of the order of D squared parameters involved in this family, which you can tweak in such a way that these conditions are satisfied. But still, you will have a family of states which are defined. So for instance, in this case, for 4x4 case, there will be around 16 parameters. So we'll have a 16 parameter family of PPT entangled states in a 4 tensor 4 system. And this is very interesting because till now people have only managed to find examples of states which only have one free parameter inside or 2 free parameters inside and very special form. But here basically we'll have a lot of freedom in the parameter space. We have of the order of D squared number of parameters if we are in D tensor D system, and we can freely change them as we like as long as these conditions are satisfied. And you can also expect that as the number of vertices increase, so for instance, if you consider a 5-vertex graph, 5 vertices, then the number of patterns, number of graphs which are triangle free will also increase, right? And similarly, so this increase is substantial. So let me move on to the final part. So since the number of triangle free graphs increases dramatically with the number of vertices, and hence correspondingly the number of triangle free entangled families that you can construct will also increase, right? So this is a sequence of the number of graphs that exist for vertices D equal to, this starts with the 4 vertex graph. So in 4, when you have 4 vertices, there is only one triangle free graph that you can consider. And mind you that I am not considered a subtlety in this entire business. So for instance, you can imagine that if you have 4 vertices, this graph, let's say you connect these two with a line, this is also triangle free, right? Because there are no triangles inside it. But we need to get rid of these certain instances of pathological graphs. But I am not talking about it here. You can look up the paper if you want to know more about this. But the point is that as the number of vertices increase, the number of triangle free graphs increases as well. So in just a 15 tensor 15 system, there are around 10 to the power 10 distinct triangle free graphs, and corresponding to each one of them, you can construct a corresponding family of PPT entangled triangle free states by following the procedure that I just elaborated, right? And you can see how quickly this number grows. And so you can imagine in a 100 tensor 100 system, there will be an astronomical number of families of PPT entangled states that you can consider. So this is the fascinating aspect of this entire business. The fact that there are these billions and billions of families of PPT entangled states, which have not been uncovered, which people have no idea that they even exist. And this formalism of triangle freeness and positivity and entanglement and all that we discussed here, this allows us to unearth this new kind of entanglement, which is crucially dependent on how zeros are distributed on the diagonal of the matrix. What is the zero pattern of the diagonal of the density matrix that you started with? And the final point is that if you try to apply the usual methods of if you try to find, let's say, a witness for the state, the witness in the sense of positive map, right? So there are classical algorithms. So you can, I think I mentioned this yesterday, you can open up MATLAB. There is a package called QuestLab inside it. It has a function called isSeparable. It inputs a density matrix and then tries to compute whether or not this density matrix is separable by using the best known classical algorithms. So I have tried this a lot of times. If I input a state which is triangle free in that function, then it just runs for around 30-40 minutes, and then it just stops. It terminates and says that the algorithm is not able to determine whether or not the state is entangled. Because in order to do that, it will take probably 100 or a million years or something like that. So classical algorithms that we currently know, they basically rely on searching within the space of uncountably many positive maps. You have to search for a very specific map which detects the entanglement present in the state, right? And that is an arduous task, right? And so the usual traditional methods of entanglement fail miserably in this regime. But in contrast, in order to apply this technique that I just mentioned, you just need to, see the matrix, collect its diagonal entries, check whether it's triangle free. This can be done in 1 or 2 seconds. Then you need to you connect the B and C matrix and check whether it's positive semi-definite. And there are very fast algorithms to do that. So the entire triangle free detection strategy works in the order scale of seconds, 1 to 3 seconds. So that is the speed up that we have from the usual strategies that are present. But notice that the domain of applicability of these results are severely restricted, in the sense that you can only apply this when the given state is triangle free. And there are lots of examples of states which are not triangle free, obviously, right? So there is a trade-off, but that is what we have, right? Okay, I guess that's it. Thank you for your attention. If you have any questions on any of the things that I covered, I'll be happy to answer them.
I have just one question. Can you go back to previous slide? So in, the reason we are severely restricted to triangle-free graphs is because of the fact that the companion matrix of dimension 2 is a the theorem holds only for dimension 2, right?
Right.
And we are somehow in this case, like you said, the two adjacent indices, and it works out like that.
Right.
Okay, that makes sense.
So a possible direction to extend this result would be to consider new kinds of graphs. Let's say, what's special about triangle free graphs? The special thing is about the D equal to 2 comparison matrixing, right? Let's say we want to extend this to new kinds of graphs which are square free or pentagon free or whatever shape that you can imagine. And then try to see if we can formulate a similar result for those classes of graphs. But then for them, you need to, for those kinds of graphs, you need to analyze the comparison matrix thing, positivity, and so on. And that's not very easy to do. For D equal to 2, so triangle free is in that sense very special because it is only considering 3 vertices. And if there is no triangle, then you can be sure that the vectors have support less than or equal to 2. In this case, the comparison matrix thing works. For higher case, I mean, there is certainly a possibility of generalized versions of these results to exist for higher or more exotic kinds of graphs, which are square free or whatever free.
Yeah, so I don't have further questions, but this was very, very fun. I had a lot of fun. So thanks a lot.
Thank you for attending, man.
Wonderful. Great.
Are there any other questions? Okay, and the references, these are the couple of few references that were used here. This is a very minimal list, and there are lots of others. So in particular, this paper in 1989 by Werner, this is where this definition of separability was first conceived in this paper. So he calls these states EP, Einstein, Podolsky, Rosen correlated states, which are entangled or something like that. And so this is where this notion of separability was first defined. This was the paper where the positive.
We have a raised hand.
Okay.
Go ahead, Shanshu.
Yeah. So, like, if you have any follow-up questions or queries, like, can we contact you via email or something about
sure
this?
thing, yeah. So you can contact me on Discord, or you can get my email from this paper. So feel free to contact me by message, email, or whatever.
Okay, thanks.